Scientist Smith here. We are about to have a great science show. We are going to explore the states of matter. Everybody say matter, matter. I'm going to be saying a lot of vocabulary words for you to follow along with. And remember, research these words if you don't know them. Today we're going to be talking about states of matter. Who knows the 3 states of matter? If you know them, say them out loud. Solid, liquid, and gas. Exactly. Solids, liquids, and gases. So for instance, this is a liquid, right? Right? This is a liquid, right? No, couldn't fool you. This is a solid. Solids, we can see solids really, really well because a lot of the matter that makes solids up are really, really packed in, really, really tight together. And there are a lot of them forced in, for instance, a structure that we can see, such as trees, such as this table, this cylinder right here, my styrofoam bin, and all sorts of other solids. I'm sure there's a lot of solids around you right now. Go ahead and look around the room and see if you see some solids. Also, we have liquids. For instance, this is water. We all are familiar with water. Liquids. There are some other liquids that I have around. For instance, this is Styflo, liquid starch for our clothes and to make science projects, which we'll get to a little bit later. Here's another liquid. Vinegar. We're all familiar with vinegar. Here's one. Glue. Glue is a very, very special liquid because it's what's called a non-Newtonian fluid. We'll get to that a little bit later. But liquids are all around us as well. We drink liquids, we use liquids for all different types of things. Now, gases. Gases are really, really, really small particles, small matter, things that really, really microscopic that we a lot of times can't see unless they're cooled down or warmed up. For instance, clouds in the sky. They're very, very cold, condensed water molecules that are packed in and condensed really, really tight. And then once they're fully saturated, it starts to rain on us. Liquids. Now, gases, liquids, solids are all around us. As a chemist, which I'm a chemist, we create different types of things that we utilize every day using the periodic table of elements. Everybody say, element, elements. Elements are what make up the world. There is a periodic table of elements that has all different types of elements that we are familiar with and use every day. For instance, 2 that we utilize all the time is hydrogen and oxygen. Hydrogen being the first element on the periodic table, it is very, very lightweight and flammable. But when you mix it with oxygen, the oxygen mixed with 2 hydrogens make what's called water. And that's very, very safe. Water. Now, solids, liquids, and gases, I can go on and on and on. Today we're going to talk about how solids mix with liquids to make different things. And then there are liquids that mix with gases to make different things. For instance, this right here is what we call slime or gack. But as a scientist, we call this a polymer because it's made of many parts. Polymer. Say that word. Polymer. Polymer. There are all different types of polymers on here on this table. This is a bottle, glass, excuse me, not a glass bottle, plastic bottle. Over here, this is a plastic container, Tupperware that we are familiar with. This is also plastic, a polymer. Most polymers are comprised of plastics and different types of plastics as well. There are all different types of thickness, some that are bendable. For instance, this top right here, look, it bends, it's bendable. But this right here is a little bit more stiff and rigid, and I can't bend it as much. This right here, this polymer, as you can see, I'll bring it a little closer to you. Check it out. It's a little windy out here. There's water in there, so that doesn't go flying around. But as you can see, look, it's wiggly. This started out as 2 liquids. So this solid was once 2 liquids. The 2 liquids that I have there mixed in with a little bit of extra solid borax solution. This borax has an ingredient in it called sodium tetraborate. And that sodium tetraborate acts as a binder to congeal and what's called cross-linking the liquids together. So the 2 liquids that I had was liquid starch and glue. But glue is a non-Newtonian fluid, so it acts like a solid and a liquid at the same time. For instance, right here you can see that it's crusted. See? It started to solidify. Say that word, solidify. Solidify, that means it's turned into a solid. So I'll pull that off there. Look, that is liquid glue that was, for instance, stuck to the side of my container, and you can see it's now solidified. It looks kind of like a plastic, right? Because it's that type of material, polymer. Now this, as you can see, it was like wiggly all around. You can make this more stiff if you increase the concentration of our sodium tetraborate. Liquid starch right here is very low concentrated in sodium tetraborate. So that's why when you use this, we have polymers that end up being a little bit more stretchy and elastic. Say that word, elastic. Elastic. Rubber bands, elastic. Now we'll go on to another activity that you can do at home. For instance, this is cornstarch and water. Now what we want to do with this is add water. Move my gloves out of the way so that you all can see. And this is a great experiment to do. Adding water slowly. By adding water slowly, you allow the solids to mix in very well. And you can also see how some of the solids and some of the liquids are starting to mix and turn into a different type of mixture. So as I stir it like that, oh, that was green. So green and blue. No, green and red. Yeah, green and red. So as you can see now, it's a lot of liquid. I obviously put too much water in there because look, I used my screwdriver here, and look, it's just water. It's liquid. That's what it looks like. Just looks like milk, right? But watch this. Oh. I take some more cornstarch, and now I'm increasing the concentration of cornstarch. So say that word, concentration. Concentration. That means the ratio of liquid to solids. For instance, now look at it. You can see it's starting to stiffen up. I'll get a clump out, and look now. I can pull up a big clump of it because I've increased the solids that's in our mixture here. And eventually, I'll be able to poke at it. And right now, you can see that this goes all the way through. That's only because there's not enough solids in here. If there are more solids in here, the solids then work together to condense and act more like a solid. The solution will do so. So now I'll take this, and now look at it. It's giving me back some resistance as I try to stir it because there are now more solids in here than liquid. So our material, now I can probably use my hand. Watch this. So now that liquid that we had, as you saw, was now, look at it. It's liquid there, but as I clump it and give it some pressure, you can see that it starts to solidify still. So it's acting like a solid when there's pressure on it. Say that word, pressure, pressure. So when you apply force, which is pressure, when you apply force to it, you can see the solids start to stiffen up. But if you let them relax, you can see now they're acting more as a liquid. But as I split it right there, you saw me split it, it's solidified, but now it's also a liquid. So I'll let it rest, and you can see as it wiggles down, it's acting like it's dripping, right? But it's actually a solid and a liquid at the same time. Non-Newtonian fluid. Say that with me. Non-Newtonian fluid. It's a pretty weird color, but now take this, and now look, it's a ball. So I'll roll it and keep rolling it and rolling it and rolling it, and as I'm rolling it, I'm giving it energy. Say that word, energy. Energy. I'm applying a type of energy called pressure or force. As I push up against it, it pushes back. The solids are pushing back. But as I let the molecules and the elements that make this up relax, you can see now See how crumble it? See? Liquids should not be able to do that, but it's crumbling like snow because I'm applying a force, a pressure to it. Yeah. You can try that at home with adult supervision, of course, and this is cornstarch and water, so theoretically it'll just wash right off you. But look now, and I'm stabbing at it, and you can see, look, but I can push up, oh, pumped out. But you can see it's wiggling. So I'll turn it upside down now. You can see kind of, I don't know if you can see it, this is good. I can turn it upside down and nothing happens, right? See? Nothing's happening. See? Solid. But it still has some wiggle in there because there's still water trapped inside of our solids. But if we were to add more water to this, what would it do? What do you think it would do if we were to add more water to this? Right, it would get more concentrated with water, thus act like a water solution opposed to something more solidified. Good job. All right, so we started out with some solids and some liquids. Let's move on to solids and liquids at the same time. Just like we had our solids and our liquids here, this didn't create any type of reaction other than what's called a physical reaction. Say that, physical reaction. Physical reactions always end up with the same products that you started out with. For instance, we started out with water and cornstarch here, and we ended with the same thing, water and cornstarch. Nothing was created. What we are going to do now is when it starts to cool down. This is another experiment you can do at home with the safety and supervision of an adult. All you need is an empty bottle, some vinegar, some food coloring to make it more fun, and a balloon. A balloon. All right, so we talked about solids and liquids. Now we're going to go to a little bit more gas action. Everybody say the word gas. Gas. I don't think we did liquid or solid. Let's say liquid, liquid, and solid, solid. All right, we got them down. Now we're going to go to gas. Gas. So gases, which are blowing me away right now, all around us, microscopic particles or molecules or elements or atoms. These are all different ways of saying the type of material, such as a matter or a liquid, gas, or solid. Now, nitrogen is an element, oxygen is an element, or what else are some elements you know? You have some actually in your kitchen right now. We put them on the grill. We put them to wrap up our food. You're right. Aluminum. We have gold. We have copper, titanium, argon, krypton, magnesium, manganese, lithium, which are in our batteries and in our phones and in our computers. I can go on and on. What we're going to do is open up our vinegar. Remember, under adult supervision only, take our vinegar, pour it into a separate container so that it's easier for you to manage and you won't have to waste it. And you won't have to, if you're adding food coloring, add food coloring to the entire container. What I'm going to do now, add a green juice, green food coloring. You can see as I stir it and I make it a mixture that is all green. I'll bring it closer so you can see a little bit closer. All green. Ooh. Very nice, very nice. Green liquid. All right. And what we're going to do is just transfer this green liquid into our bottle here. Transfer. A little laminar flow. All right. Now we have our liquid. This is vinegar that is now green. And I'll set that there. Actually, let's set it in here just in case. Baking soda. Where's my baking soda? Baking soda, baking soda, baking soda. Baking soda! I got it. So now we're going to take our baking soda. Another option, you can use baking powder if you have it. It's the same. It'll do the same thing. Remember, rubber bands and balloons are polymers that are elastic. So what you want to do is open this up as much as possible. If you're having help, you can open it like that and have someone pour it in. I'm out here by myself, so I'll just do this. See, make like a cup and use my spoon or utensil, and in goes our solids. Solid as a rock. All right. Now I'm gonna come a little closer so you can see the two mixtures here. Boom, boom. So we have our two containers. One container has our liquid. One container has our solid. Now, just a little bit more Excel science. This vinegar has another name. It's called acetic acid. Acetic acid. Try to say that. Acetic acid. Good job. Acetic acid, and this is our baking soda or baking powder, whichever one you have. This also has a different name. Sodium bicarbonate. Try to say that. Sodium bicarbonate. All right. This liquid is going to cause a reaction known as a chemical reaction. Now, when you have chemical reactions opposed to a physical reaction, chemical reactions create new products. Remember, physical reactions like our oobleck over here, we didn't create anything new. We already started out with cornstarch and water, and when we ended that reaction, we had the same thing. Mentos reactions, Mentos and diet soda or any type of soda, those are also physical reactions. You're not creating anything new. That carbon dioxide gas already existed in our soda or whatever beverage that you started out with, carbonated beverage. Look. Whoa, B. Whoa, B. B. What, B? Oh, it's a what? I'm doing a science show. Thank you. Peace. Huh? All right, back to the show. All right, so acetic acid, acid-base reaction. What was I talking about? Oh, the physical reaction of the diet soda with the Mentos. That reaction is a physical reaction because we started out with our gas, which was already trapped in our soda. Right here, our gas that we're going to create is trapped in our bicarbonate, and our acetic acid is going to react with it and create carbon dioxide gas. Now, we breathe out carbon dioxide gas every day. Try to breathe out some. I have a balloon here. Now, we can't see that gas that we blow out of our mouth, right? Try to see it. Can you see it? No. The only times we can see that gas is, for instance, in temperatures where usually for us, when it's cold. When it's cold outside, we can see our breath because our hot breath condenses in a cold environment, which is the outside, and creates clouds. Smoke. Steam is the same thing, but in reverse. Hot molecules going into a cold environment, and they start to condense. But we don't see steam that often because steam then warms up and those molecules start to disperse into smaller particles that we can't see, and they warm up. So this gas that I'm about to put in my balloon, we can see because it's going to be trapped in the polymer. See? So now there's gas in here, and we can see it now because, for instance, this is colorful. We can see the color. It's a solid. We can see the solid because there's more parts to it opposed to that gas that I just let out. The molecules are so tiny that we can't see them. There's gas molecules flying through between me and this camera right now. We can't see them unless it was cold outside or there was moisture, water in the atmosphere, such as fog. Now we have this balloon, and just to show you that this balloon has something in it, and that thing that's in it has a lot of energy. Gas molecules are really, really fast and bounce around, bouncing around. That's how they're spreading out and expanding this balloon. But if I let it go, you can see that the gas had to go somewhere. That gas had to go somewhere. Now, the same thing is going to happen here. When we create this gas, it has to go somewhere. This gas got to go somewhere. So what we're going to do is just take our balloon and stretch it around the top right there. We don't want our solids to get in there just yet, because we want to make sure that it goes down solid. Solid goes down solid. So what we're going to do is open it up like that, hold it, so that you can make sure that it's nice and snug, tight right there. And remember, in science, nothing is created nor destroyed. What we have here is acetic acid, sodium bicarbonate. When they react together, they create a new solution, and the solid that is now in that solution creates gases. The gas is carbon dioxide gas. Carbon dioxide, say that, carbon dioxide. All right, here we go. You can see, look, as I slowly add it, you can see now, look, there's gas starting to be created, and there's bubbles. You see the bubbles, but now I'll let a little bit more go, and as I add more solid, more gas is then created. And look, it's starting to bubble up and bubble up. Now it's really reacting with that liquid. And as it reacts more and more, that chemical reaction is creating our carbon dioxide gas, which is inflating our balloon, increasing the area that is expanded in our balloon. Because remember, our balloon is elastic. So this balloon, I'm the one providing the gas. For this balloon, the liquid mixed with the solid provided the gas to create this balloon. Expanded, just like this one. But that balloon flew away. This balloon's not flying away because the elasticity around here is snatching and trapping around this container, creating what's called a closed system. So since this system is closed and the balloon that I just let flying is not closed because I let it go and it was open, that gas is trapped inside right here. See, it's trapped. So safety first, safety first. Put on my cryo gloves here. Now, we talked about solids and liquids and solids and gases and solids. Now we're going to talk about liquids and gases. So this liquid, here we go, liquid nitrogen. Woo-wee. Liquid nitrogen. So that liquid nitrogen is already physically reacting with the atmosphere. The atmosphere around us is what's called warm, compared to the liquid nitrogen, which is negative 300 degrees Fahrenheit. That's 300 degrees below zero. So with it being so cold, it cools down the things that are around them or the things that go in them, such as my breath. As you can see, it's condensed all of my breath into a cloud of gas. Now, this liquid could be mistaken for water. That's why in science, we never eat or drink in science. Remember that. We never eat or drink in science. Why? Because you can mistake easily a solid for some type of candy or food, and you can easily mistake a liquid for a beverage that we will consume on a regular basis. For instance, this right here, this looks like some good old green soda, if there are green sodas out there. Yeah, green soda. But we don't want to drink this because it's vinegar and baking soda. For one, it would be very nasty and it would be very damaging to your stomach. Your stomach is already acidic as it is. So I'll take some liquid nitrogen and pour it into my cup here. So this liquid is turning into a gas. The liquid is not stable out here in this environment because nitrogen, the element, its natural state is stable as a gas. So nitrogen makes up about 78% of the air that we breathe. So out here, most of this air outside is nitrogen gas. Say that, nitrogen, nitrogen. I'll bring it closer so you can see. Nitrogen, nitrogen. So nitrogen gas makes up most of the air we breathe. It's good also for our soil, for those who are gardening. Yeah, nitrogen's awesome. But this nitrogen right now is evaporating. Say that word, evaporate, evaporate, which means turning into a vapor or turning into its natural gaseous state. This liquid is really, really tiny as a liquid. As a gas, the nitrogen molecule grows 7 times its size. So as it turns from a liquid into a gas, it expands. It grows bigger and bigger, taking up more space. I'll show that to you right here in my container. So I'll take some liquid and pour it in there like so. For instance, while this liquid is doing its thing, I'll show you that this liquid is doing the same thing that that cup is doing, but that cup has an open top. This top can easily be popped off. And if I let it pop, see, it'll pop itself all the way off, because remember that gas takes up space. Matter takes up space. Matter is everything that takes up space, fills a void, whether it's a liquid, solid, or a gas, or even a superheated gas, which is called plasma, electricity. That's the fourth state of matter. You'll learn that a little bit later. So this gas is starting to create pressure. Everybody say, pressure! Pressure! That pressure built up enough force to push off that top way over there with the help of the wind, of course. But look, it's also that liquid and the gas, as it expands, changes the temperature of my container, just like it changed the temperature of my cup. And as you can see, look, it's like ice or snow on a nice sunny hot day, right? Now, how do we do that? Because there's water molecules that are all around us out here, really, really small water molecules that condense onto the cup because the cup is so cold. With this cup being so cold, the water molecules stick and hug and attach themselves onto the cold surface, such as frost or snow or ice cubes, water particles condensing. Everybody say condensation, condensation, condensing. So if I look at my glove now, and then I take this and rub it on here, now look at my glove. So all of that is water that was really, really cold. And then this will eventually warm up, see? And as it warms up, it just now looks like my hand is wet. But inside of here, the liquid, see? That liquid nitrogen. Doing this liquid, I'll pour some out here again. I have a hot dog, hot diggity dog. So look at the hot dog now. It's wiggly, wiggle, wiggle, wiggle. So now I'll take that and stick it on in here. I'll wipe the sides so you can see what's going on. But look, it's bubbling now. And the reason why it's bubbling is because we put that hot dog inside of a cold container. And it's starting to react. It's starting to react. It's starting to react with our hot dog. Now our hot dog is eventually going to start to get really cold. And as it gets cold, it's going to start to become brittle. And as you can see, it wiggles up here, but down here, look, it's now condensed. Has condensed water molecules on it because it's hard, like an ice cube. So I'll take it and I'll flip it upside down. So you can see, look, I'll try to squeeze it. I'm squeezing it and nothing's happening. I'll take the other side and put it down in there. So our styrofoam is so lightweight that it was starting to fly away. Some molecules are very lightweight, some molecules are very heavy, depending on what type of element it is. There are a lot of different elements on the periodic table that weigh more than others. This is just a periodic table of Mario, Super Mario Brothers. But here, a super periodic table, a real one. See? This is one on my lab coat. Google one and see how the weights are different and all the different things that create an element. So now, this hot dog, look, listen to it now. Listen to that. This hot dog started out like this. See? This is the original hot dog. Original hot dog. Uh-oh. See, look. It doesn't have as much vibration coming back off of it as this one because this has become more of a solidified structure. This is more of a wiggly, and you also have to think, this is not frozen. So with this, what's called lukewarm or room temperature, the molecules that make up this hot dog have started to relax. Opposed to over here, they're rigid and stiff because they firmed up and stiffened. Hot dog. So take this and I can pour this over there, and it'll evaporate back into the air. So this, I'll take my hot dog and look, Right there in the middle is starting to thaw out, see? But right here, look. But right here, look, it's starting to thaw out. And if I blow on it, I can increase the thawing process. So now as I blow on it, my breath is so hot that it's starting to warm up and relax these hot dog molecules. And now it's starting to wiggle a little bit more. Eventually, this will go back to its natural stable state. Right now, it's unstable. Remember, different types of molecules have different stabilities. So right now, this is stable. This one, look, this one's not stable at all. This one's still rock hard. Take this back of a So now look at it. Hot dog for all of these crumbs, they were that one hot dog. And now, listen. See? Hot dog. Elephant toothpaste. Elephant toothpaste is a decomposition reaction. Say that word. Decomposition. Decomposition. So this reaction is dealing with hydrogen peroxide. And hydrogen peroxide naturally decomposes as water and oxygen gas. Of course, we know oxygen gas. We need it to survive. The trees give us oxygen gas in order to survive. We breathe in oxygen gas and we breathe out carbon dioxide gas. Now, when we breathe out that carbon dioxide gas, it helps out the trees. What we're going to do now is create our catalyst. So our catalyst solution is made up of water and potassium permanganate. So potassium permanganate is our catalyst. Everybody say catalyst, catalyst. So a catalyst speeds up reactions, chemical reactions. So this case is our lovely, beautiful purple potassium permanganate. I'll bring it closer so you can see. It is windy, 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 windy. All right, so here's our potassium permanganate solution. And just give it a nice stir. We have our potassium permanganate right here. This is our catalyst solution. This is going to speed up the reaction of our decomposition. We're going to turn this hydrogen peroxide into water and oxygen. Now, our oxygen is a gas, and our water is a liquid. Now, how are we going to trap gas bubbles? We are not going to use a balloon. What we're going to do is use soap. So soap is the best way to trap our gas bubbles. And what we're going to do is take our potassium permanganate solution, pour it into our potassium permanganate in our vessel. We have our soap. Let's put soap in here also. Make sure that gets nice and well mixed. Soap. And hydrogen peroxide is commonly found at 3%. So if you have hydrogen peroxide, it's usually found in a brown bottle because if you add heat to it or light to it, it speeds up that decomposition process. And your hydrogen peroxide would just be water after a while. And the gas bubbles in there, once you open it, it's just oxygen gas that releases back into the atmosphere. My hydrogen peroxide, however, is 35%. So that means there's more pure hydrogen peroxide in my solution here. So for instance, if we were in a 100% solution, this is 35% hydrogen peroxide and the rest of it is 65% water. So there's more water in here, but there's also more hydrogen peroxide. Hydrogen peroxide is very dangerous and corrosive. I'll show you a label. So in chemistry, we have scientists, they follow different procedures following these different labels. So these hazard labels, as you can see, all mean different things. This one, what do you think that means? What do you think that one means? This is a caution one. This one, let me see what that is. This is for immediately wash your hands. This is an oxidizer symbol. There's also another oxidizer symbol. For instance, if you're in the packaging industry, you see this a lot. For instance, if you're at UPS and you deal in the hazardous hazmat industry and ship different types of chemicals, corrosive is another one. And as you can see, they have these different numbers. These numbers are different types of classifications. This is an oxidizer classification, and it lists the different types of things oxidizers do. This is a corrosive classification, and it also lists the different types of things corrosives do. So corrosives, they break down and corrode things. Corrosive. So say that, corrosive. So corrosives break down different things. For instance, hydrogen peroxide breaks down a lot of different things. Oxidizer means that it oxidizes different types of things. Oxygen is very, very important for flames, fires. That's why there's a fire right there. So this would increase the ability for a flame to continue or even grow tremendously or even explode. That's why it's very important to follow these labels and to practice safe. Now, we have our solution. This looks like some good old bubbly soap water, but it is not. It is merely hydrogen peroxide that will burn you or me, so I have my gloves on. Y'all ready? And I'm gonna pour and let it fire away. Because remember, the gas bubbles are gonna instantly be created. And as they're instantly created, our soap is gonna trap them. And our soap is going to create what's called suds that we're all familiar with. Those suds and bubbles are gonna create a big giant foam that a lot of people like to say looks like elephant's toothpaste because it's so big. Sun's coming out. Sun loves science too, y'all. This is living proof. Living proof. Sun loves science. All right, here we go. The sun is science. It's our number one source of energy. Science. All right, here we go. You ready, son? I'm ready. All right, y'all ready? Y'all ready? Here we go. 5, 4, 3, 2, 1. Whoa, whoa, whoa. Look at it. It's still foaming. Got a lot of foam on my table here. That's okay. All right, that's science for you. Our hot dog is back to normal. Hot dog is back to normal. It's a little still a little stiff, but it's back to normal. Back to normal hot dog. Next, we're gonna expand some liquid nitrogen. Liquid nitrogen. Now here's a great way to show you that molecules, for instance, this gas molecule or these gas molecules, they don't go anywhere unless you allow them to. So right now I put that balloon in my styrofoam bin, which remember has our liquid nitrogen in it. Here's another balloon. It'll stay in there. Wind's blowing it around. There we go. And let's use this balloon. Since, remember, this is our balloon that we created carbon dioxide gas with our vinegar and baking soda. So we'll use that balloon also. Put that in there. Ooh, and here's another balloon. Looks like this is going to pull air into oh, let's try that again. All right, let's try that again. Here we go. Round 2. Always have a backup, ladies and gentlemen. Always have a backup. All right, here we go. Pop. Oh, it ain't gonna pop on me this time. All right. All right, cool beans. Cool. Boom. So I'll take that, stick that down in there real quick. And you can already immediately see the reaction that's going on, physical reaction. So physically, the gas molecules inside this balloon are starting to decrease in temperature and energy. So remember, gas molecules are floating around, bouncing around real fast, but as the temperature starts to decrease, that energy also starts to decrease. And they do not have enough energy to bounce around and expand. But once up, as you can see, the gas molecules inside are warming up, and they increase their ability to expand the balloon because they have more energy, more heat, more fire, more fire. Now this balloon, look at this one, flat as a pancake. Flat as a pancake. I'll bring it a little closer so you can see. Flat as a pancake. Take this one out, you can see the balloon is not as inflated as it was. But now as it warms up, it starts to reform as the shape that it once was. This I'll take over here. Right there. Now this, take out the first. And remember, these gas molecules have force. They have power. They have energy. They have ability to expand. And I'm just holding it gracefully. But as I come closer, you can see that it starts to push itself out of my hand. It's pushing itself out and re-expanding. See? Now we'll take some water and expand this nitrogen into a bigger cloud. At the same time, changing this water into ice because the temperature of our liquid nitrogen is so cold that it's going to decrease the temperature of our water. So for instance, this water right now is very, very warm or hot. But when I put it into this cold environment, the temperature change is going to turn this water into ice or solidify the water. Say that, solidify. So this liquid nitrogen is going to turn into a gas. It's going to evaporate. Say that word, evaporate, evaporate. So this water is going to turn into big condensed clouds. Here we go. Y'all ready? And, like the sun's coming out again. Coming out, son? All right, here we go. In 5, 4, 3, 2, 1. Woo! Got a little water on me. Let's go. Got a little wind. All right, so you can see it's going round. It's evaporating, expanding. So this gas is water that is freezing now and condensing as there are other gases around. That is condensing and cooling off the air. But as you can see, it starts to disappear over here once it gets past that table because these gas molecules are warming up. And as they warm up, they spread out further apart. Now, I'll show you. There's a little water there. Pour out the water or liquid, excess liquid. Now, watch this. Look inside of there. See that? It's ice. Ice, ice, baby. See? Ice. That ice right there was our water. Started off as our water. Now, it's ice cube. Ice cube. See? Ice. Oh, here's one final explosion for you too. Enjoy. Here we go. In 5, 4, 3, 2,